All right, so in this particular video, we're going to now foray into another application of integration. We've covered some basic applications of integration in the class so far. Maybe the most complicated one we've covered is, volumes of revolution. But now that we're kind of learning more techniques, it's going to allow us to unlock executing certain types of integrals. And so one of the most common places that you're going to see integration in the real world is going to come in the presence of your STEM courses, specifically like physics, engineering, chemistry, things like that. And so the very first application that we're going to learn about is the concept of work from physics. And so the beginning of this video is going to be a little bit of just an introduction to the theory behind what work is, and how to calculate it, and then we're going to dive into the nitty-gritty details of maybe some more challenging examples. So from physics, work is defined to be, or rather maybe instead of a colon there, we'll just say work is equal to the force applied to an object times the distance that object moves. Okay. Now in physics, force is usually described using the unit of a Newton. Okay, force is applied in newtons. This is if you're in the metric system. So maybe I'll write metric. Right, force is in newtons. You may have also seen force more commonly if you're in America as pounds of force. Right, so if you step on a scale, this is the imperial system. And that's the unit that we use to measure force in America. And then for distance, again, for the metric system, we tend to use meters. But if you are in America or use the imperial system, maybe they'll use things like feet, miles, etc. Okay. And the idea is, let me paint you a picture. Let's make this the ground, and let's say that there is a box. Now, we're going to have to imagine this box is like infinitely small, that it kind of represents one sort of particle that we're trying to move. But so maybe you can imagine there's a dot in the center, and that's what this box is supposed to represent. But let's say, that you're here, and your job is to push with your incredibly long arms this box. Okay. Now, if I want to push this box and I'm exerting an amount of force, okay, this particular force here has to be going in the direction that our box is traveling. So, in the future, you may encounter examples where you're applying a force at an angle, right, with some kind of angle theta of which you're pushing down in the box or up in the box, and you're going to need to figure out which part of that force is actually going in the direction that we're traveling. But if I want to move this box, okay, a certain amount of distance, so this part here is going to be, let's say this is 10 meters, and if I am pushing this box with 15 newtons of force. Okay, so I'm using my muscles, I'm pushing on this box with a constant 15 newtons of force. The question might read, for example, if you push a box 10 meters with a constant, and I'm going to underline this because this is going to be interesting to us later, with a constant force of 10 newtons, or not 10 newtons, we said 15 for this example, 15 newtons. How much this word work is done on the box? Is done on the box. Okay. And the calculation for this is as straightforward as it sounds. We're going to do the 15 newtons multiplied by our 10 meters, and we're going to get 150 Newton meters as our answer. Now, if you've taken physics before, or maybe you've watched a couple science videos of some sort, you may recognize this unit, Newton meters. It is more commonly known in science as the unit of joules. And joules is a measure of energy. So if it helps, you can think about this when you think about work being done on something. You can think about it as the amount of energy required to move this box. Okay, so this is all fine and dandy, right? The process for doing this is fairly straightforward. The idea of calculating work seems to make sense. But the problem is that in the real world, right, it is very likely that as we're pushing this box, we're going to encounter different stretches here that maybe have different amounts of friction and are going to require different amounts of force. And so the next question that we have to kind of answer is, what happens if the force being applied, right, varies, right, at each point. Okay, and so what do I mean? We're going to erase some of this. So let's say that we're still going, our 10 meters. Let's say that from start to finish, this is going to be the 0 meter marker, and to the finish, there's the 10 meter marker. But the problem is that if the force that I'm exerting is no longer constant, if I'm pushing this way, but now my force is going to be represented by a function, we'll say f of x, okay? And the idea is that let's say that I'm at this particular x right here, so right, my box is right there, then the amount of force that I'm going to be applying right at this instant is going to be very different than the amount of force I'm going to apply, say, maybe over here at like some second x value, right? These two amounts of force is going to be different. So the energy that I'm going to be, required to move this box is going to be different at each of those instances. And so just like our concept with calculating total volume before meant adding up a whole bunch of tiny volumes, or the concept of finding total area meant adding up a whole bunch of tiny areas, the idea is that I can no longer just do this whole calculation in just one stretch. And the idea is that I have to consider calculating all the little tiny works that's required for every single x value here, right? That I cut up my interval into infinitely many tiny pieces, and I say, okay, in this little interval, how much energy do I need? In this little interval, how much energy do I need? In this little interval, how much energy do I need? In this interval, how much energy do I need? And we're going to add all of that up. So maybe I'll write down that total work means that we're going to add up all of the tiny works, right, at every point. That's the idea. And for where are we going to do it? Well, for this particular example, we're going to do it from 0 to 10. And so the idea here is now, okay, well, all I need to do is to come up with a formula for these tiny works. And work is still force times distance, right? It's still force times distance. But now the force that we are exerting, it varies, right? This force is given by the function f of x. And the question is, well, how far am I going to be pushing the box, right? If I'm talking about, the box when it's here, am I talking about all of the energy it takes to push the box, the rest of the distance? And the answer is no, we can't do that because the force changes at every single one of these points. So I can really only talk about exerting my force for this little tiny little bit of distance here. And guess what we call that infinitely small, really, really small, tiny distance there? In this particular example, we're going to call it dx. And so we get our force times our distance, which in this case is dx. And so it turns out that a work integral For this particular example, and there are different ones for different examples, but for this particular example, it's going to be just as simple as saying that we're going to add up all of the tiny works, which is going to be our force function, f of x, over a tiny distance, and we're going to do that for every single x value from 0 to 10. Okay, and so this is our force, this is our distance, and we're going to do this. And so we could use this formula. So, for example, let's stick with the box problem, but let's say, for example, so we push a box with a force represented by f of x equals x squared plus 3, a total distance, actually here, instead of just saying a total distance, we'll just say from x equals 0 meters to x equals 10 meters, how much work have we done? Right? How much energy have we expended? How much work have we done? Okay, and so this integral setup is very simple. It's going to be the integral from 0 to 10. We're going to pop in, right, the fact that our force varies, right? We already logicked our way through it. It's going to be x squared plus 3, and then, the dx, and each one of these is going to be the amount of force it takes to move that box one tiny iota of space, or excuse me, how much energy it takes to move that box one tiny iota of space, and we're just going to add them all up. So in this particular case, we get x cubed over 3 plus 3x evaluated from x is equal to 0 to x is equal to 10. Since when I plug in 0, we're just going to get a bunch of zeros. We just need what we get when I plug in 10. 10 cubed is 1,000. And then 3 times 10 is 30. And we could get common denominators here. So if you want, we could say this is 1,090 over 3 Newton meters of work, or if you prefer, joules of energy. Okay, and just to check that our units line up, right? This is our force function, which means this is in newtons or in pounds, and then the dx over here, that's a measure of distance, so that's going to be some tiny little bit of meters. All right, so that wasn't too bad. Let's see. Let's do a slightly different example then. Okay, so for example, so let's say that we have a 200-pound cable that's 100 feet long, is hanging off the edge of a tall building. So it's hanging from a building. And the question, kind of like maybe if this represented pulling up an elevator or something like that, right? It's hanging from a building. How much energy is it going to take to pull that cable up to the top? Okay, so how much work is required to pull the cable to the top? Okay, so let's make a drawing and let's see if we can kind of do some reasoning for ourselves. So we have a cable. This cable is kind of hanging down. It's chilling. It's 100 feet long. So we're going to say this is 100 feet. All right. The cable itself weighs 200 pounds. Okay. Now, something that I want to point out is that pounds is a force, right? So this is already the force. And the reason why I'm pointing this out is perhaps an aside, which is that from physics, force is equal to mass times acceleration. Okay? So when we talk about the metric system and we say newtons, right? Mass is usually given in kilograms, and the acceleration that we're talking about, it kind of depends, But if, for instance, we're talking about like, the force exerted by our bodies on the ground, or something where the only force or the only acceleration is due to gravity, gravity is given to us as meters per second squared, typically for the metric system. And so this is how we get our units for newtons. When it comes to pounds is also a force. We've already taken into consideration our mass. Now, for the imperial system, mass is in this ridiculous unit called slugs. And then acceleration is usually in feet per second squared. So at the very least, we found some common ground in the second squared, but pounds is measured in this. So, if you want to talk about your mass and you want to say, I have a mass of 58 slugs or something like that, you could do it. This is the imperial unit system. But the point that I'm trying to make with all this stuff is that pounds already incorporates the force due to gravity and the mass of the object. So there isn't any extra consideration that needs to be taken. They're already giving us that information in this problem. Also, as an extra aside, if this happens to be the acceleration due to gravity, usually we use 9.8 or 9.81 meters per second squared. Sometimes you can round this up to 10 meters per second squared. The question should specify which one of these to use. I usually use 9.81 for a little bit more precision. And then for feet per second squared, depending on who you talk to, this is approximately 32 feet per second squared is usually the unit, but usually a problem will specify if they need you to take into account the acceleration due to gravity, they're going to give you those things. So I just wanted to give you those things to have kind of in the background of your mind and to help you try and remember that pounds are already a force like newtons. They've already been calculated. So I'm going to leave this kind of over here. But let's get to actually answering this particular question. So our goal is to do work. And so, again, total work means that we're going to add up all of the tiny works. And here's the idea, right? So again, we're adding up all the tiny works, which is force times distance. And here's the nice thing, right? The nice thing is that the force doesn't vary. The force is 200 pounds for the entirety of this cable, which means that the force is also, if we wanted, is that since the entirety of the rope exerts 200 pounds and it's 100 feet long, we could say that there is that each, or we could just make the ratio even, that 200 pounds of force is being exerted over the course of the 100 feet of the rope, which implies that there's a ratio of 2 pounds for every 1 foot of this cable. Okay, so that's nice. That's not too bad. But what's varied this time, right? Because it's not right. This part of the rope and this part of the rope and this part of this cable, right? They all they exert the same amount of force, right? Gravity is acting on this small chunk of the cable in the same way that it's acting on that small chunk of the cable, in the same way it's acting on that small chunk of the cable. But the thing that is different is that each of these pieces, I have to pull up a completely different amount depending on where they start. So for instance, pulling up this bit of the cable is going, if I were to just isolate this as a point, is going to take much less total energy than it is this one, because even though they exert 2 pounds per foot of force, I need to pull it up way longer if that piece ends at the bottom. And so when it, so again, we're back to this idea, just like in the last example, where we cannot look at this, the cable in its entirety all at once. We kind of have to split it up and talk about these tiny works, or how much energy is it going to take to move this thing section by section. So let's say that we are at a particular, say I'm at some particular x value. Or actually, just to spice things up, let's make this a y because we're going up and down. And so the question that I would ask is, okay, if I take a small chunk of this cable, how much work is it going to be to pull it all the way to the top? And I'd say, okay, well, first and foremost, the distance that I'm going to have to pull that bit of cable. In this case, the way I've labeled it, I'm going to say y. I'm going to label it in such a way where this distance is y, and the top would be 0 meters. Now, you don't have to do that. If you want to make, say, your distance from the ground y, right? If you want this to be y, then you could make the remaining distance, right? This chunk here would then be, well, if the distance from the ground up to to here is y, then the total distance that we have left over would be 100 minus y. So however you decide that makes most sense to you, you go right ahead. But I'm going to choose to label this little slot right there y. And I'm going to say that this distance here that I have to go is what I mean when I say that's at y. So the distance that I have to lift this box, this little chunk of the cable, is y. But the force being exerted on it, well, okay, so let's see. The force being exerted, okay, well, we know there's a ratio of 2 pounds, right, per foot, okay? But this is not 1 foot of cable, right? Like, for instance, if this was 3 feet of cable, then we would say there's we would just multiply this by 3 feet to get there's 6 pounds of force being exerted. But if this is only a tiny, 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 tiny chunk of the cable, then this is not 3 feet, it's not 10 feet, it's not 4 feet, it's dy feet of cable. So times dy feet. And that is going to allow us to complete our integral. So for us, we're going to have our 2, right? Our 2, well, what's our unit going to be? 2 pounds, if you will, times y, and our distance is in terms of feet. And then what are the bounds for y going to be? Well, we need to take a slice for all of these particular y values. We can say starting at y is equal to 0 and going all the way down to y is equal to 100 based on how I have this drawn. So from 0 to 100, and we could execute this, right? We could do this. So we're going to get 2y squared over 2, which is just y squared, evaluated from 0 to 100. And I think 100 squared is 10,000 foot-pounds. Right? You might see this unit as foot-pounds of work. But again, this is just going to be joules of energy joules are Newton meters. I didn't just say that. This is a unit of energy that we could convert into joules if we converted properly from feet of feet into meters and from pounds into newtons. Okay. I do want to point out that, in the instance that I had said, what if you are in the camp of people that choose to mark this in the following way? So what if you call this y, but you want to say y equals 0 is down here and y equals 100 is at the top, and you prefer this method. So you want to say that this distance here is y, and the rest of the distance would be 100 minus y, right? Because if this is 100 and this is y, well, 100 minus y is going to give you what's left over. So let's set up the integral that way. So in the same way, I'm going to say we're going to have the integral. We're going to add up, again, my force times distance. And a lot of this is still going to be the same, where we're going to be doing the integral of, all right, so the force being exerted, that is still going to be my 2 foot-pounds per tiny little chunk of rope. And then the distance, though, is the thing that's going to change. That's one thing that's going to change, which is my distance that I have to cover for this particular chunk is going to be, well, it's going to be this gap, right? That's the distance that I have to go. So it's going to be 100 minus y. And then my bounds, well, I'm still taking all these slices at various y values, so we're still going from y is equal to 0 to y is equal to 100. And this looks like a very different integral, right? I have 2y over here, I've got this thing over here. Let's evaluate it all the same. Let's do it. So we'll have an integral from 0 to 100 of 200 minus 2y dy. And then, so this is going to be, let's see, 200y minus y squared, evaluated from 0 to 100. And I believe that if we plug in 100 for these, over here I'm going to get 20,000. And then I get 10,000 there. And then when I plug in 0 into both of these, I'm just going to get 0, so minus 0. And this answer is still going to equal the 10,000 foot-pounds of energy that's required to lift this cable. So in both ways, you get the same exact answer. You just need to be a little bit careful with your units and how you are choosing to make this drawing. So as long as you're consistent, you can draw it any particular which way. So I'm going to stop this video here. The next video is just going to be a couple more examples of work, but I think these ones are a good couple of examples to really get you kind of into the idea of this. And in an effort not to make this video an hour long, we're going to split it here. So this video is going to cover the easier examples. The next video is going to cover maybe just a couple slightly trickier examples, and then you should be good to go. So hopefully that wasn't too bad and that it's making sense. And when you feel like you're up to snuff, let's head on over to the next one.